Welcome to Reinforcement Learning, and now we're gonna see how we can solve for the best policy in each state directly. So we have seen the value iteration algorithm, and the idea of the value iteration is to optimize the value function by getting better and better estimates of the value functions for each state, and then at the last step extract the induced policy to see what policy is the optimal one. Now the question is, can we directly operate with the policies and optimize them? The answer is yes, we can use policy iteration for this. Now, how does policy iteration work? Policy iteration alternates between two steps. So one is it tries out the policy and calculates the value function for this policy in a policy evaluation step, and then it improves that policy to get another policy and try out what the values are here, and then it improves again, and then it evaluates again, and so on and so forth. So the first step is the policy evaluation, where we have the value function for a given policy. It doesn't need to be necessarily the optimal policy, and usually it will not be the optimal one. But essentially, we have this v pi of s here on the left-hand side and also on the right-hand side. And what we also do not have here is this maximum. So it's not maximizing here. It's just evaluating what is the value function of this policy. And it's evaluating this by using Gaussian elimination, for example. So it's an exact value, and it's not an estimate like in value iteration. Now the policy improvement step that looks at which is the best policy, or can we improve actually the policy given our previous policy that we had and the values that we had here. So then we extract a new policy based on the v pi that we have evaluated for that policy. Now the summary of the policy iteration algorithm looks like follows. So we initialize the algorithm to any policy in the beginning. Then we evaluate, so by solving a system of linear equations, this Vn, which is on both sides here, by doing these analytical calculations, we get a value function for each state given that policy, and then we do an improvement step where we take that value Vn and see whether we can do better and change our policy in the next period. And if we change that policy, actually, that means that we have found a better policy, and we repeat it until we don't change that policy anymore. So we cannot improve further, and then we are done and we found the optimal policy. Now, looking at our example where we were the startup that was poor and unknown and wanted to be rich and famous, we did the value iteration, and if you remember, we had to do many steps and get many estimates of the values for each state in order to find the optimal value of these states and the optimal policy. Now, we can also solve this with policy iteration. So we initialize the policy to, let's say, invest in the case we are poor and unknown, invest when we are poor and famous, invest if we are rich and unknown, and also invest when we are rich and famous. So invest, 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 invest everywhere. So now, if we calculate here the policy evaluation, we get a plus 10 for rich and famous, plus 10 for rich and unknown, and a 0 for the two poor states. And now we can try to look at whether in this case we can actually improve our policy and get a better value out of that. And actually we can do so. So if we for example change here to safe in the rich and famous state, and also safe in rich and unknown, and poor and famous, but we keep the poor and unknown on invest, then we get, if we solve the system of linear equations, we get these numbers here. And if we then try to improve, we will see that there is no chance to improve anymore. We get the same numbers, so we are done here. After 3 steps, we are already done. And so how does this work, the policy iteration? The key essential ingredient is that we have monotonic improvement. So if we have 2 different policies, they are associated with 2 different values, Vn and Vn plus 1, in 2 consecutive steps in the iteration, then this Vn plus 1, so the next iteration step, must be better or equal to the value at the current iteration step. So why? Because we know that the best policy, if you evaluate, use the policy evaluation operator H for the best policy, then this is going to be better than the policy evaluator at the policy, some policy pi n. So then we can actually also extract the policy pi n plus 1 from just taking the argmax of the reward vector plus the discounted expected rewards in the future, and then we can just plug in. Yeah. So here this H star is then this reward vector for the policy pi n plus 1 plus this discount factor times the transition rate for this pi n plus 1 times this Vn. And here we have Vn then on the left hand side here and also on the right hand side. So we want to isolate that Vn. So we take this term here to the right hand side by subtracting, and we are left with this rewards of the policy pi n plus 1. And they are greater or equal to this identity matrix minus gamma times this transition matrix for policy pi n plus 1 times this Vn. And now we can take the inverse, and here we have the definition basically of the value function for the iteration n plus 1, and that's gonna be better than the value function of n. And that's basically what we wanted to show. Now, this shows that there is monotonic improvement. If we go more steps further in the policy iteration, we will have a better value function. And now, actually, theorem 2 shows that the policy iteration actually converges to the optimal value function and also the optimal policy in finitely many iterations when we have a finite state space and a finite action space. Now the proof is that, well, we have just seen in lemma 1 that the next iteration will give us a higher value function than the current one or an equal one. And since we have finitely many actions and states, there are also only finitely many policies that we can try for each of the states. And so the algorithm will terminate in finitely many iterations. And so when we don't have a change anymore in the policy, then we have found the optimal value function, and this Vn actually is then equal to the next iterations Vn, and then we can stop, because that's equivalent to the Bellman equation where we have then found the optimal policy. Now, doing value iteration is costly, and how costly is it? Per iteration, we have this number of states squared times the number of actions which are determining the costs. How quickly is the value iteration converging? It's converging quite slowly, so we have many iterations that we need to take and have linear convergence. Policy iteration, however, is a little bit different. So in terms of complexity, it might be even more complex because we have to solve a system of linear equation which has complexity, cubic complexity in terms of the states, which are the dimension for which we solve in the system of linear equations, plus the squared number of states times the number of actions. So in policy iteration, we have fewer iterations, so we converge more quickly. Early on, we have a linear convergence, and later on, we have a quadratic convergence. And here, quadratic convergence is better than linear convergence. We converge more quickly. Now, given this complexity and convergence properties, it's not clear which one is better, value iteration or policy iteration. So we can actually combine both to have something called the modified policy iteration algorithm, which is the best of both worlds. So here we alternate again between two steps. But the steps are now a little bit different because we only do a partial policy evaluation up to k times. So we try k different policies and solve for the optimal for the value functions of these policies, and then we do policy improvement after the k steps. So we don't necessarily go through all the possible policies, but we just do some of them, then we do policy improvement, and then we go back to the policy evaluation. So that's the algorithm. So we initialize the policies and the value functions to anything, and then we repeat k times this policy evaluation, where this is solving the system of linear equations exactly to get a Vn. And then we take this Vn and see whether we can improve that by taking another action and improve the policy. And if this value function in the next iteration then doesn't change anymore in terms of threshold epsilon, then we stop. So this is similar to what we have seen for value iteration. And essentially, the same theoretical guarantees also hold for the modified policy iteration, like for the value iteration, namely that we have our estimates. We don't have the actual values here that are the true values, like in policy iteration, but only estimates because we stop at some point. And the distance here is gonna be less or equal to epsilon over 1 over gamma, like before for value iteration. And then if we have here this error, then we might get a worse policy actually and make things worse and get 2 times this error over epsilon over 1 minus gamma. So the proof for this is in this book, so you can read it up. And what we have seen now is that the complexity of value iteration is quadratic in the states times the action. So here, lower complexity would be better. But the convergence is quite slow, so we have linear convergence here. The policy iteration it might be more costly because we have to solve this linear system of equations and have also this number of states squared times the number of actions. So linear and between linear quadratic convergence is what we have, but we have fewer iterations, so it's much more quickly that we converge. So the modified policy iteration is in any case better than each of the two other algorithms, because here we have complexity that is only k times the number of states squared plus number of states squared times the number of actions, and we have something which is between linear and quadratic convergence, so few iterations. And essentially, if k is equal to 0, then we are doing value iteration, and if k is larger, then we are essentially doing policy iteration. So here is some references to read up on this, and let's summarize what we have seen. So how does policy iteration work? Policy iteration is an algorithm that can actually directly work on the policies and ensures monotonic improvement. It converges infinitely many steps, often in the order of only 10 or something really small, for finite Markov decision problems. And it gives the optimal policy and the optimal values function for the states. Modified policy iteration actually combines the advantages of policy iteration on value iteration and needs fewer iterations than value iteration, but is each step is more costly because it solves the system of equations. So that's it for this unit. Thanks for watching.